All right, I'm gonna just got some stuff to go through today. I got 3 proofs I want to talk about. I've got some extra homework problems, so that's one additional homework problem that I just gave you a handout for. I don't know if I like our book. Honestly, I don't think I would use this book again. I would go back. I've been using this other book, Abbott, for like forever since I started here, and I was like, let's shake it up, and I'm going back to Abbott next time. These books are from Abbott, or these problems are from Abbott, and so yeah, let's see. So I had a few problems that I did want to assign. I don't think I did last time. Did I give you homework last time? No? Okay. What the fuck? Did I write this down? Oh, yeah, here we go. So these problems, homework, 11.5 and 11.10. And then the ones that I just handed out. And I would recommend to read chapter 11. There's a lot of little details in there that would be helpful. And you know, a good thing to do, a good thing that I've been learning to do is everybody has access to ChatGPT. Honestly, the $20 a month is pretty much worth the advanced model for sure. We pay $20 a month for like Netflix and shit, right? So this is like an actually useful tool. But what you could do is you could either give it a PDF of the chapter, or maybe you have a PDF of the chapters already. I don't know. They're probably readily available. Feed that to ChatGPT and say, hey, can you turn this into simpler language for me, or give me the highlights of this? And it will do an incredible job. So like you can take all your textbooks and just turn them into something that's more in your own language. I've been doing that a lot, honestly. It's a great way to use AI. So yeah, so these, and then the Bolzano-Weierstrauss problems. And these are going to take a while. This, you do not, like, I'm going to say let's collect these on Wednesday after break, so we can at least talk on Monday after break. Please don't wait till Tuesday after break. Because this shit, like, these are brain teasers. These are not easy. And a couple of these are not easy here. So, like, seriously, just give them thought. Read them. Give them some thought, set it aside, and do that a few times throughout the break. I think it'll pay off. So I beg you to do that. Your mileage may vary on how you take that advice. Is there anything you all have on your minds? Break. That's what I got on my mind. So, cool. All right, well, I've got 3 things I want to talk about today, 3 results, and then we'll do the quiz. And if we get done early, so be it. So, first off, yeah, so 3 results today. And this first one is a theorem. I forget what it is in our book. But every sequence contains a monotone subsequence. 1 minute, look at that. Notice there's no mention of boundedness. There's no mention of convergence. Just a sequence, just a list of real numbers. And no matter what that list looks like, inside of it, we can select a monotone subsequence. We can select we can select points from there, a subset of points that either don't go down or don't go up. And they might go all the way up, and they might go all the way down, but we can find this monotone sequence. This proof is actually pretty tricky. And so I'm going to go through the constructions, and we're going to stop at the major construction in this proof. So let's let x sub n be a sequence. And of course, the unspoken is of real numbers. I don't even know if I hit record. Probably. Yeah, thanks. Let x sub n be a sequence. Define the set M. So define M to be the set of all indices n. Now this is the part that's hard to get your head around. So we're gonna talk about this. The set of all indices n such that a sub m is greater than a sub n when m is greater than n. So write that down. Just take a minute, read it a couple of times. Because it's pretty non-trivial. Looks simple. But I think the only way to really get your head around this is to look at some examples. At least that's how I got my head around understanding what this thing is. So we're going to crank this out for a few generic sequences. I'll let you finish getting it down. We're going to just look at some examples. We're going to see what M looks like for each of those. Once we understand this, the proof becomes easy. But understanding this is not easy. So let's just make up some sequences. So this is going to be 1, 2, 3, 4, 5, 6, 7. This is going to be x of n. This is going to be n. I'm not going to put exact values, but I'm going to make things look either above or below each other. And when it's in doubt, I'll put a little colored line on the board to make sure that it's clear what's happening. So first off, let's go kind of straight. And I'm going to pick this sequence where as I move to the right, I constantly go down. So think, like 1 over n kind of sequence. 1 over n-ish kind of sequence. So let's figure out what M is for that. So M is the collection of all n so that for that term, that nth term, everything past it is bigger. So let's take a look right here. We're going to ask ourselves, is n equals 1 in that set M? So this is A1 right here. And so what we would need for that to be an M is we got to ask ourselves, is A sub M greater than A sub 1 when M is greater than 1? No, you're shaking your head no. How come, Cormac? I agree.
Going down.
Because they're less. There's nothing to the right of this term. So this says to the right of. This is to the right of. There's nothing to the right of it that goes up. So 1 is not in there. Is 2 in there? Now, give everybody a second. So I'm seeing some head nods to the right. But let's definitely. So the question is A sub 2, are there any elements of the sequence? Shit, this should say, sorry, let's make this A because now it's not like I'm using the book notation and my notation screwed up. Are there any sequence elements bigger than A2 as I move to the right? And you can see that no, there aren't. Nothing ever increases here. Notice that it also is for all. There's an written for all to the right. So for everything to the right, it has to be bigger than this guy for that index to be in there. Same thing with A3. A3, there's nothing to the, if I move to the right of 3, everything's less than it. So I would need everything to be bigger than it to be in this set. So what we can conclude here is that the set M for this sequence is empty. There's nothing in it. And we can consider that finite. There's just empty set is a finite set, has 0 elements in it. Let's look at another one. Hold on, so let's see. I did a bunch of these last night when I was thinking about this. Let's do this. So what I'm doing here is I'm making a sequence where here's 1, here's 2, here's 3, here's 4, and then after that it's kind of just an oscillation, like a plus or minus 1 kind of situation, but tiny in this little strip up here. I don't want these to look like they're getting closer together. So let's figure out what M looks like here. Is 1 in M? And so you ask yourself, I see the correct head nod. I ask myself, to the right of this, is everything above it? And the answer is yes. So 1 is definitely in there because all the sequence values to the right are bigger than A sub 1. What about 2? Is 2 in there? Is everything to the right of 2 above this level? So 2 is in there. What about 3? No, because as I move to the right, the very first thing is less than it. Is 3 in there?
Did you say they were getting closer together?
No, they are not getting closer. In fact, I want them to look like plus minus 1, so kind of a constant. So no, right? Because as I move to the right, that's up, but that's the same level, so it's not greater than it. So here, and let me just draw red lines to kind of help emphasize that these are all on the same level. Let's try another one. So here I want you to think 1 minus 1 over n-ish. And maybe these are approaching some sort of limit up there. As I move to the right, they get closer to that line. What is m here? Take a minute. Think through what is m? Hold on, don't say it out loud. Think. Oh, do you have a question?
A little bit.
Yeah, ask your question.
So, does this mean, like, could you extend that theorem to say that, like, every sequence contains a monotone non-decreasing subsequence?
No, because no.
Okay.
Because the set M isn't giving us the answer. It's part of getting us to the answer. So don't, this is just going to be a tool. Notice that this sequence here, Christian, this sequence is definitely decreasing, non-increasing. It's just that M was empty. So this M isn't the answer to this question. This M is a tool to help us answer this question. And we're going to look at two cases. We're going to look at the case where m is finite, and that's going to give us non-increasing sequences. And when m is infinite, that's going to give us the non-decreasing sequences. Or excuse me, actually, the strictly increasing sequences, subsequences. Does that help get your bearings a little?
A little bit, yeah.
Yeah, this is weird. Camila, what do you think m is here?
Do you make it like infinity? Or like do we?
It's all of them. Every single thing is in here. So it's the whole natural numbers, because here's a sub 1, here's 1. That's in there because everything to the right is bigger than a sub 1. A sub 2 is in there because everything to the right is bigger. A sub 3 is in there because everything to the right is bigger. So here I have an increasing sequence, and that's going to say that m contains everything. Let's look at another one. Because, like I said, this is really the way for us to understand this. So let's say that that's a sub 1, that's a sub 2, that's a sub 3, that's a sub 4. What's m here? You're looking for a place. You're in M if your index, if you are less than everything to your right. There can't be anything below you to be in M. So we're just grabbing the indices of those things. Liv, do you feel like you got this one? It's okay. You can try.
Yeah, I was thinking like it'd probably be like 2 and 4, maybe.
Oh yeah, actually, yeah, I hadn't even thought of it. So this guy's definitely not in there because this stuff is all lower than it. So 1 isn't in there. But 2, definitely everything to the right is in there. So, excuse me, above it. So I agree with you. It's 3. No, not 3, but then 4. And then what else maybe?
Probably like 6, 8.
Or 5, even these kind of like, right, they kind of, so like from there on out. So yep. Good job. Let's do another one. What have we, let's do one more. What do you think, Courtney?
Empty set.
Empty set. We see that? And again, M is empty. Remember here, N was empty. So like here, we had a sequence that was strictly decreasing. Nothing ever went up and stayed up. Here, you ask yourself, is there anything to my right that's above me? No. Is there anything to my right that's, to my right is everything above me? And the answer is no. So I was saying that question wrong. To my right is everything above this level? No. To my right is everything above this level? Nope. A lot of stuff is at my level. And here we're defining this to be strict inequality. So M is empty. One last one. what's M? Camille, you feeling good on this one? Empty, empty. That's what you got. Okay, cool. I couldn't quite. Yes, M is empty. Do we all feel that way? There's no point here where everything is above it to the right. Started off good. If this had done this, if this had leveled off like this, then this would have been an M and this would have been an M. But it didn't happen. Cool. All right. So we at least have a vaguer understanding of the set M. And the only way to get that is to do these very specific breakdowns. So now, once we understand that, I think you're ready for this proof. So what we're going to do is we construct this set M and then we look at it. We're going to have case one. I often say don't do cases in here, but this is one of those times when cases is just perfect. So this is actually a very beautiful proof. M is finite. Let's think about the case, the times when M was finite. M was finite right here. M was finite here. M is finite in this newer version here. And what that means is that you've got stuff that is not strictly increasing eventually. That at some point things aren't always going up. So we'll say M is finite. So let's say M equals M1, N1, let's not. Let N1 be the first index greater than all the indices in M. And we can find that because it's a finite set. So you could actually even say that N1 is equal to the max of M plus 1. So I go to my list of M, like right here. Let's actually do it for this example. So let's see here, M was 1, 2, and then that's it. So here, N1 would actually be this guy right here. Does that make sense? That's not an M. Okay, since N1 is not in the set M, I know that I must either stay at that level as I move to the right or drop down. Because if from here the only place to go was up, it would have been an M. If you are an index where to your right, all you do is go up, then you are in M. But we're saying, let's pick the first value that's outside M, and we know that it's not an M because somewhere to the right we stay at the same level or we drop down below that level. So, since N1, is not an M, that's what I meant to say, so put a slash through that, is not an M, there exists some N2, which is greater than N1, so that A sub N1 is greater than or equal to A sub N2. So I either stayed equal or I went down. since n1 is the right edge of M, it's past the right edge of M, everything past there is not in M. So make a little note here. Note, all n greater than or equal to n1 can't be in M. So n2 is not in M. Since n2 cannot be in M, there exists an n3 that is to the right of n2, such that a sub n2 is bigger than or equal to a sub n3. In other words, I can move to the right and find something that's at my same level, or it went down. And now I have an inductive loop here. So continue that process forever. You can always move to the right and find someone to your right that didn't go up. They can't be, because there's no one to, there might be someone to your right that went up, but no, because yeah, there might be somewhere to your right that's not up, but not everybody is up after you. Otherwise you'd be in M. So continuing this process, create a list of subindices n1, which is less than n2, which is less than n3, less than blah, 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 where a sub n1 is bigger than or equal to a sub n2, bigger than or equal to a sub n3, bigger than or equal to. So we have a non-increasing monotone sequence. And we have constructed a monotone, non-increasing subsequence. I saw this proof and I was like, I can't do this one before class this morning, so I spent a lot of time last night making sure I got this shit down. Christian, is there anything I can help you with at all, friend?
No, I think I'm just gotta sit with this for a second.
Yeah, it's heavy. I mean, it's kind of heavy in a way. It's a weird construction. That's case 2. So case 1, when M is finite, we have a non-increasing monotone subsequence. Case 2, M is infinite. Remember what that looked like. When M was infinite, that meant that at some point, so this is, yeah, well, I can't put the end of M because it's infinite. At some point, everything is above you. So if M is infinite, this would be like the first entry in M, right there. The place where the sequence starts going up forever and ever. So if M is infinite, choose any n1 in M. That's going to be our first index. Then a sub n1 is less than or equal to strictly less than a sub n for all n greater than or equal to n1. That's what it means to be in here. To be in M means everybody to your right is bigger than you. So that's N1. So that means I can easily find an N2. Just pick any one to my right. Choose any N2 that's bigger than N1. Then, just because of this, A sub N2 is bigger than A sub N1. And everything to the right of n2 must be bigger than a sub n2. Blah, blah, blah. Now we're at this inductive thing. So continue on this way, just choosing any index you want to the right. There's lots of ways to do this. This is not a unique process because I can choose whatever I want. I could come up here and go, here's N1, and then you know what, that's N2, and then that's N3. But I've got myself an increasing, continuing this way to produce a strictly increasing subsequence A sub n k. Monotone. So when m is infinite, we've got monotone strictly increasing. When m is finite, we've got monotone non-increasing. That's got the constant cases in it, and it's got the decreasing cases in it. That's a cool proof. That's pretty wild. Like, whoever thought that up? And I actually think it's pretty recent, this proof. I mean, math recent, right? Like 100 years old maybe or something. All right, so that's the worst thing I got to show you today. The rest of it's pretty easy. The rest of this is pretty chill. Let's just knock out the big easy one right away, but remember we've got some major theorems, and one's on the quiz today. We have the monotone convergence theorem. What does that say? Just a quick practice for the quiz. In your head, think, what does monotone convergence theorem say? Cecil, what's that say?
Any bounded monotonic sequence converges.
Any bounded monotonic sequence converges. Beautiful. Monotone convergence theorem. All right, it doesn't have the word bounded in it, but that's the thing we got to remember. Beautiful. So knowing that and knowing this is going to be essential for moving forward after the break. So this theorem is called the Bolzano-Weierstrauss. There's only two S's. Theorem. These are our powerhouse tools. These are our jackhammers and our table saws. And you get the point. I'll stop bringing up examples of big power tools, but these are them. I'm gonna wait till Christian's ready. I don't want to start. You're good? You sure? Okay, cool. So Bolzano-Weierstrauss theorem says this. Any bounded sequence contains a convergent subsequence. It's so beautiful. I think we can work through the proof together. Let's get us rolling here. Let's let x of n be a bounded sequence. Now here's a hint, and I want you to take a minute and see if you can do the proof for this yourself. You know everything you need to know. You also know the monotone convergence theorem. Can you put that together with what we talked about today to get a proof, an elegant, beautiful two-line proof for Bolzano-Weierstrauss? I think you can. you go. That's it. And here, I would actually I would pull this apart into, just to say, and we know that every sequence contains, right? Just to make sure, like make it sound like you're citing something, you know, that's all, but you got it.
Is there an N for?
Yeah, I gotta look in the book. It's a good question, Corbett. There's no fancy name like.
It's like Theorem 11.
It's something like that. There's no like cool Moss's theorem or anything like that. It's Theorem 11.3. Actually, that proof came out in 1982. Yeah, that's like yesterday. Math. And since I don't want you to be bored, Corbett, so I'll give you the next thing if you want to kind of work on it. Or whoever's done. And I don't know what you're writing at your desk. It could be love letters. I have no idea. Love letters to Bolzano or Weierstrauss or both. So theorem. This was something I mentioned last time. If x sub n if sequence x sub n converges to L, then every subsequence x sub n k converges to L. What's that?
It's a little bit.
It is. It's yeah. There's. You need this little trick in it. You need that in it. But can we go? Are we cool to go through this Bolzano-Weierstrauss proof? Camila, do you think like you got an argument here?
I think
Yes, ma'am. What
so,
you
but I
got?
feel like I'm missing something.
It's okay. Let's talk it.
So if we have a bounded sequence, we know that by the monotone convergence theorem that any bounded sequence converges.
Not exactly that. What is? Tell me. What does
Any
MCT
bounded
say?
monotonic.
Yeah. So, but I don't know that this itself is monotone, right? But how could I get a monotone? Subsequence. So you're on the right track. So I've got x sub n as a bounded sequence. How about this? Let me get you on here. We also know that any sequence x sub n, so let's not think about bounded
The
for
one we just did.
yeah, exactly. Contains a bounded. I see black. Now I'm going there.
Monotones.
A monotone subsequence x sub n k. Now I'm going to apply the boundedness to it. Does that make sense? And then we're done. Since x sub n is bounded, every subsequence is bounded. Making this a little wordier. So, by the monotone convergence theorem, x sub n k must converge. What's that? That is an interesting smile.
Well, I'm confused about
Let's talk.
how you can apply boundedness to the subsequences, specifically like with the example of 1 minus 1 over n. Like that's a bounded sequence, right?
Correct.
But doesn't the like subsequence go to like positive infinity?
This is a great conversation. So let's talk. So let's actually look at this guy, right? It starts at 0 when n is 1. Then we go to a half. Let's make 1 right there. Then we're subtracting off a third, so we're 2/3, 3/4, and we approach that asymptotically.
Yeah.
Is that all sounding right?
Yeah.
Okay, cool. And we get closer and closer. So now, what were you saying about? There's a subsequence in there that does what?
That would go to positive infinity, right? Because like everything, like that sequence is non-decreasing, right?
Correct.
So for any like m, there exists like for any m, like every n greater than m.
Yeah, what is m here?
1 or
So 1's definitely in there because everything to the right is in
Yeah.
there. Is 2 in there?
yeah,
Is 3 in there?
yeah.
What's
Like,
in there, Christian?
wouldn't it be like just everything?
Everything.
So that's kind of where I'm confused because that does not seem.
You are, and this is what I was thinking.
sets
So
and
you're
sequences.
confusing the indices with the values of the sequence.
Oh, okay.
The boundedness is about the horizontal strip. Does that make sense? So like you can see here, everybody in here is between 0 and 1. There's no sub-collection I can pick that's gonna fly off to infinity or minus infinity.
That makes sense.
Does that make sense?
Mhm.
Awesome. That's what I was thinking you were kind of thinking. You were like thinking about infinite this way
Yeah.
versus infinite this way.
That makes a lot more sense.
Awesome. Yes. You are right. The indices are unbounded. 100%. But they will always be unbounded.
Okay.
Well, except if n is finite. But for all the sequence work we do, you've always got an infinite list of things.
That makes sense.
Yeah?
Yeah.
Okay, cool. Any other questions on this? Let's make sure we're cleared up. Beautiful, beautiful, beautiful. So, really elegant proof. That'll be on the next quiz after the break, for sure. Let's do this one together. Cormac, did you crack this at all? Nope. Okay, fair enough. It's not. It ends up being kind of simple, but you gotta. It's tricky. It's tricky. So this is the last thing we're going to do today. We might probably get out early, and that's not a problem, I'm sure. If the sequence itself converges to L, then so does every subsequence in that original sequence. So proof. Let's assume that sequence x of n converges to L. Really quick, practice writing out the definition. What does the definition mean? Or how do you write that with epsilons and good stuffs? Hope we're there. If not, one more chance to remember it for the quiz. I'm gonna assume we're there. So we know that no matter what epsilon is, we got this. So let's do a little scratch work of what we need. We need, given epsilon greater than 0, we need to have a place in the subsequence. So let's talk about that subsequence. We're going to produce a subsequence that looks like this. And it's working with these indices that's the hard part of this proof, these double indices kind of going on here. So we need this given epsilon greater than 0 to show there exists some, we're going to call it capital K, just to help us wrap our brains around it, such that when K is bigger than that capital K, that's looking pretty Gothic and Greek, capital-like, we have x sub n sub k minus L is less than epsilon. So think about what's moving in this subsequence. It's this little k down here, because we don't know what n1, n2, and n3 are, but we know they're cooking. So the moving part is that little sub-index there. Okay, so let's let x sub n sub k be any subsequence. Could look, well, looks exactly like this guy right here. I don't know if it's monotone, I don't know anything. Doesn't have to be. Then since, now here's the trick. K is less than or equal to n sub k. And remember I talked about that at the in last class. So this was just for last class. You might want to go watch that again, or read about it, or go to ChatGPT and say, explain to me, like I'm 5, why this is. I like to, and I'm not being condescending. I literally do that shit all the time. ELIF. This, like a 5-year-old could get that, but I don't think we're going to do this at the Warner Elementary tomorrow.
Fair enough.
Probably, yeah, fair enough. We're going to stick gumdrops with toothpicks. Then, since this happens when k is bigger than this n right here, we have n sub k bigger than or equal to k greater than n. So this n right here is this n right here. These are the same n. And I'm just saying, as soon as I pick something bigger than that, I know that this happens whenever the index is bigger than that capital N. So this is just a different index, and it's bigger than or equal to its little sub-index. So since this happens, it follows, now you know something probably hard to wrap our heads around is about to come. It follows that x sub n sub k minus L is also less than epsilon. Just saying, pick an index bigger than n. That's an index bigger than n. I already know that I've got that property up there. I'm good to go. These subsequences, these just move you out further. So if I know, for example, that, the 10th term, if I know that big N is 10, then I know if I know that this is true when N is bigger than 10, then it's also going to be true for the 11th term in the subsequence, because this is past the actual 11th term in the sequence, possibly. It could be equal to it, but it's certainly not to the left of it. I feel like the more I say about it, the worse it might get. So tell me if there's anything I can do to clear that up, because this is our proof. Therefore, so they use the same n. I'm just going to use this n that I used up here for the subsequence, subindex. Therefore, x sub n sub k converges to L by the definition of convergence. Because I've produced, for my call epsilon, I produced a response. So, same response for epsilon as the original sequence. That's it. And that's all I have for you today. which is enough, and we'll do the quiz here in a minute, but I want to reiterate. This page of problems, these are on the homework for next Wednesday, whenever, 2 weeks from today. Ooh, that sounds nice. Second half of the semester is always crazy. We all know, man, it goes so fast after break, and it gets so beautiful outside. I don't know if we could ever have class outside. We could figure out a way. It sounds like might not be good though. I don't know. Help me figure out how to do it and I'll make it happen. This page of problems, these 4 examples I asked you for, these are I think only one of those might be like not that brain twisty, but you're gonna have to play. You're gonna have to play a lot. These are super challenging. And also the 2 problems that I gave you out of the book, pretty challenging. Brain, yeah, they're gonna explode your brain in the best way possible. And you might come in on Monday and go, I don't have anything, but suffer. I beg you, please suffer over the break before Monday. Math suffering, that's all I'm asking for. Let's do a quiz, huh? Piece of paper, please. And then when you're done, you are free to roll and go enjoy your weekend, unless you have more math with me later this afternoon, in which case you're gonna go take another quiz, or 4. All right, so quiz. Please give the definition, and again, I'm looking for the hardcore definitions. If there's an epsilon possible, put that epsilon in. Of number 1, limit as n goes to infinity. Let's say x of n is a sequence. Equals L. Number 2, lim sup of x of n, lim inf of x of n. Number 3, state the monotone convergence theorem. Number 4, I gotta remember what was on there. Let's let you start writing. Well, if I can't remember it, then I won't put it up here. I think I made a list. Oh, Cauchy. Cauchy sequence. And monotone sequence. You know what? Let's not. I think we got it. Let's just do these 4. Merry Christmas. Slightly less writing.